let's review that a little bit then, in case we kind of forgot some of what we sort of talked about. So we will start with sort of the metabolism of carbohydrates.
Okay.
But let's just first talk about a few definitions that you probably hopefully remember from last time. Definitions about things like what exergonic versus endergonic. Can you help me with those terms?
Exergonic releases energy and endergonic
Absorbs
energy or goes out.
Right.
Into-
Requires a net input of energy, right?
What else?
So let's translate to that here. So between exergonic and endergonic, which is gonna have more potential energy in the products that are formed? Endergonic, that's really the definition. We say endergonic, it means that, we always have to start by putting energy in, we don't get much out, so that the products have more potential energy in them than the reactant started out, so it'll be the other way around. How about catabolic versus anabolic?
One breaks down.
Catabolic breakdown.
Yes, one does break down, yes. Mhm. Which one does which? Just,
Catabolic.
because that's an important thing to know.
Catabolic breaks down.
Right, catabolic breaks things down, anabolic builds things
Up.
up. Okay, good start. Let's see. What generally,
the important ones.
and just in generalities, we're just talking generalities here. What kind of reactions provide energy for endergonic reactions?
Hexagonic.
Exergonic, yes, right off the bat, yes, exergonic, right. You're scaring me, yes. Exergonic, because exergonics are going to release energy that the endergonics then can use. All right, we talked a little bit about energy cycles. Let's review a little bit about how we extract energy from carbohydrates, from carbs. So we started with a process that was called glycolysis. And glycolysis, I don't know if I really hammered you on this, but there's only one real sugar that we'll use for glycolysis, and that is glucose. Now, if you've read up on this, you know that eventually you actually convert glucose into fructose in the process of doing this. I don't care that you go through all that, the 1,6, diphosphate. But glucose, blood sugar is what we start with, right? And we talked about glycolysis involves a reaction where we're breaking the sugar in half. And we end up, what are the end products? Pyruvate. They each have how many carbons? 3 carbonates, right? Keep track of the carbons and hydrogens. That's always easy because if something has 2 carbons, it would have how many hydrogens? 4. If it had 3 carbons, it would have 6. Something like glucose that has 6 carbons has how many hydrogens? 12. That's where you get that sort of formula. It's always sort of easy to keep track of this. Oxygen comes and goes, so it really doesn't help to try to keep track of the oxygens when you're going through it. But tracking carbons and hydrogen can be very helpful. So when we break it apart in glycolysis and pyruvate, what is our net energy gain? Our net gain is 2. That's a net gain because we mentioned that you have to start by wasting 2 ATPs. They call it priming the pump. But after you get 2 out, then you get 4, so do the math. You get a net gain of 2. And then what happens to the pyruvate, our 3-carbon sugar? Well, it undergoes that transition to turn it into our critical acetylcholine here. How did we do that transition? Well, we had to get rid of a carbon. And carbon always comes and goes in what form?
Carbon dioxide.
Carbon dioxide. And anytime we break the frame apart, what do we also have to harvest off of our molecules?
Hydrogen.
Hydrogens. So anytime that we're breaking apart, like in glycolysis, we're also going to have to harvest off hydrogens. What do we call the empty taxi that's going to be shuttling these hydrogens around? NAD. And when it's full of its passenger, the hydrogen and the electrons are really the star player, right? They're the ones that have the energy. We then call it NADH. And once we have the transition reaction and turn it into acetyl-CoA, now we take it to a chop shop that we call the Krebs Cycle, or called the citric acid cycle, has a multitude of names. And we begin by attaching our 2-carbon fragment to a 4-carbon, producing a 6-carbon. Did we talk about that a little bit? No. Just so you know, does this show up on board? I don't think so. But the reason they call it the citric acid cycle, just as more of a Jeopardy kind of question, is that when we attach the 2-carbon to a 4-carbon, we get a 6-carbon sugar. And the 6-carbon basically sugar is citric acid. Same thing that you find in orange juice or any other kind of citric juice. That's why it's got its name citric acid, because it's really the first product that gets formed. How many times would this citric acid cycle have to turn to process one glucose molecule? And how did you come up with 2? That is the correct answer. I want to know how you got it.
Because there's 2-pyruvate from glycolysis.
Exactly. Does that make sense to everybody?
Yes.
So we have 2 pyruvates in glycolysis. The citric acid cycle would have to turn twice to process it. And once we finish stripping it down, how many of the hydrogens are going to be carried by NADH out of the 4? 3 are carried by NADH. How many carried by FADH?
1.
Just the 1. And now what do we do with all the NADHs and FADHs? We take them to electron transport system to get a lot of ATP out of it. Every NADH was worth
3.
3 ATPs. FADH only worth 2. All right. As we pass that electron from carrier to carrier, and it spends its energy pumping the hydrogens across that membrane, eventually we end up with a low energy electron that eventually somebody has to take in order to keep this going. We need a final electron acceptor. What is that final electron acceptor at the end of the electron transport chain? Oxygen. This is why you have to have oxygen in order to keep the electron transport system going. Because you need it to be the final electron acceptor. It is so desperate to get its hands on electrons that it will take even the low energy electrons that have already spent its energy pumping hydrogens. All right. All right. So that's good at that. And we ended up getting about 36 ATPs.
Yes.
That would be with full oxygen, full electron transport system. And almost all of it is what we call oxidative, meaning that we're in the mitochondria and using oxygen. Anytime that we get ATP regenerated outside of the mitochondria, they call that substrate level. Did we use that term? I thought I used that term, but I want to make, I'm saying, shaking head. Anytime you come across that term, substrate level phosphorylation, hello. You made it through the rain?
Yes, I did.
Good. Ramadan Mubarak.
Thank you.
So, substrate level. That's any ATP. I like to call it regeneration. that's occurring outside the mitochondria where no oxygen is needed. So for example, the ATP that we got from glycolysis was substrate level. Even the one we get, yeah. Oh, you actually might have come across in 109, can you talk about the sources of energy for muscle and the different sort of forms? You talk about like creatine phosphate. We talked a little bit about creatine waste, but if just as a reminder, like when you are doing something that just requires a brief, like quick, like a weightlifter, just like clean and jerk, that's just pure ATP. Whatever ATP is in the cell, if you're doing something that's lasting like half a second or something like that, boom, that's just pure ATP. But if you're doing something that lasts a little bit longer, you have an energy intermediate that was called creatine phosphate, CP. No? And so creatine phosphate is a energy intermediate that you would be using, for example, if you're running like a 50-yard dash. And in creatine phosphate, CP, will donate its phosphate to ADP to quickly regenerate what? ATP. And that just yields, and then plus creatine. And so this is a form of energy. Don't worry about writing this down. The whole about creatine phosphate, this is just an example of substrate level phosphorylation. That's the only reason I'm giving this an example, because it's occurring outside of the mitochondria. It's just donating its phosphate to another molecule. Okay, lipids. We talked about how lipids, the fatty acids, can be metabolized by breaking off basically 2 carbons from the end of the chain. And we call that process beta oxidation. And we end up taking that 2-carbon fragment. It goes through several steps, about 4 different steps, that end up getting converted ultimately into acetyl-CoA. And that's how its fragments end up getting metabolized, producing lots of ATP. Did we talk about that at all last time, about beta oxidation?
I think so.
A little bit, yeah.
Can we refresh?
Maybe
A little refresher.
That was a long time ago. That was like
Right?
2 days ago. My
I know.
goodness.
It's been a while.
I think you remember something from like Tuesday.
Yeah.
Oh, I don't know if I even mentioned this, but it's worth knowing, is that in like the next to the last step of producing the acetyl-CoA, there's several steps in the way, but the next to the last step is the production of something that's called a ketone. Ketones are a intermediate step in beta oxidation. So the fatty acid, it goes through several changes. It produces a ketone body, and then the ketones ultimately will get converted into acetyl-CoA in like the last of the reactions. Now, ketones are acidic. And so if you are burning nothing but fats, that means you're producing nothing but a lot of ketones, and that produces what's called a ketoacidosis. Yeah. And I'm bringing this up because some people should be familiar with this term, ketoacidosis. Anytime you're burning fats, there's going to be at least some level of ketoacidosis. At least it just comes along with it. Now, anytime you're primarily burning fats, again, you're going to have some level of ketones, a little acidosis. It can be life-threatening in conditions where, for example, your cells, in somebody who's got diabetes mellitus, for example, can burn nothing but fats since they can't have access to sugars. They can develop really life-threatening levels of ketoacidosis. But everybody who's burning like on a day fast, for example, if you're fasting for a day, many people are fasting today, then there's going to be some level of ketoacidosis that's going to occur at least until after sunset. Question?
So my goddaughter has something called ketotic hypoglycemia. I think that's what it's called. Is that similar to that?
I'm not a real doctor. I just kind of play one on TV. So I have no idea what that is.
Okay. I was just wondering.
I could make up some stuff, and people probably believe me, and that's kind of the power of that position. It's like, well, yeah, okay, but I have no idea what that is here.
What is it called?
It's like, I think it's ketonic hypoglycemia.
Hypoglycemia.
Well, hypoglycemia we know would mean that your blood sugar level is
Low.
low.
Yeah.
And usually when blood sugar levels are low, that means you have to burn something else, which means you would be developing ketones.
Yeah.
So ketones and having low blood sugar, hypoglycemia, do tend to go hand in hand, but I don't know what else is involved with that condition.
Oh, so how does she manage it? Because
It's-
with diet?
Yeah, so it's kind of like, she does have like a feeding tube also. So, she's autistic, so it's like she has problems eating certain foods, so then that's where the feeding tube comes in, so her blood sugar doesn't drop. Yeah, I was just wondering if it was like similar to it, but it wasn't sure.
It's got to have similar phenomena within it here, because anytime blood sugars are really low like that, hypoglycemia, there tends to be a ketoacidosis.
Yeah.
In many cases, if somebody's just maybe missed a couple meals and blood sugar level low, it's often not a life-threatening condition. All right, so beta oxidation. And then finally, we talked about proteins a little bit, I think. That proteins, there is a group of amino acids that can be converted into sugars and can be burned. We talk about that as being glucogenic ones here.
Yeah, because amino acids, I think you said, can't be turned into other amino acids or something like that.
Right, other ones can't be. And so you have to, when you're trying to, you can burn them. You can burn them, if you will. You just can't convert them into sugars. And the way you would have to burn them is first you're going to have to get rid of the amine portion, the nitrogen-containing amine group here, either by sticking that amine group onto another fragment. All right, they call that transamination, when you take the amine group and then put it someplace else, or you just convert it into a waste product that is urea, which is a nitrogen waste. That's almost a guarantee that's going to show up on the test. You need to know what urea is. It's a nitrogen waste, almost exclusively from the breakdown of amino acids. And again, that's from the metabolism of proteins.
Did they like give out the same questions for the final? Because it's like you, because I know, like you always like this is gonna be on the test. Like, do they like give out the same questions or something? Or
No, but
do you
there's a lot of
just
the main
know?
concepts. A lot of the main concepts are sort of similar. You know, it's like when I make up a test, I try to focus mostly on the things that at least I've heard and that I know from feedback that have some clinical manifestations, some clinical importance. You'll notice a lot of the stuff I clip about or just sort of skip over about some hormones and some compounds that are produced, and I say, oh, I'll just skip this. It's usually because I know of no clinical significance or no drugs that have it. There's no diseases that I'm familiar with that really impact it. So, but urea, you need to know that urea is a nitrogen waste product
From amino acids.
from the breakdown of
Amino
amino acids. And that when you need to burn them for energy, they're going to enter the citric acid cycle. Mostly the same place everything else by converting it into acetyl-CoA, which is why we focus again on acetyl-CoA. It is a common entry point to that Krebs cycle, that chop shop, where we're going to be stripping down, harvesting the hydrogens. That's the way I really look at that, because that's where the energy is, and all the electrons that accompany the hydrogens. Can you remind me about the absorptive state?
Driven by the insulin.
When does your body enter into the absorptive state, and how long does it last?
During the middle.
4
3 or 4 hours after you've had a meal. That's the key thing. You're going to start the absorptive state when?
3 to 4
When you've eaten something.
And then the other one won't start until you eat again.
Well, the post-absorptive state
Yeah.
will occur after you have basically gone through that absorptive state.
Okay.
So that usually starts about 3 to 4 later. The hallmark of the absorptive state starts when your blood sugar levels have dropped.
Wait, for which one? For absorptive?
For post-absorptive.
For post.
So,
After.
let's do one at a time. You're right.
Okay,
I'm going to confuse everybody here. Absorptive state is the state right after you had a meal, when you're absorbing all these nutrients, and it lasts about 3 to 4 hours, because again, that's generally about how long it takes for your intestines to process that. That's why it lasts about 3 to 4 hours. That gives you a rough idea about how fast your stomach and your intestines work. And what hormone is the dominant hormone that's mediating this process?
Insulin.
Insulin.
Oh, you're tapping that.
Oh, I was just trying to hide the word insulin from you. Shoot. Yeah, that did a lot of good. Yes. Insulin is the hormone that really regulates this absorptive state. And what are the effects of insulin? What's happening during this period? Well, insulin, is that going to have an impact on glucose uptake? Does it facilitate, promote glucose uptake? I'm not hearing everybody going yes. Does it promote? I'm hearing some of you in whispers, like you're not sure of your answer. I'll just whisper a little bit. Maybe you'll hear me. Maybe you won't. Yes. So insulin is going to increase glucose uptake. It's almost impossible for cells to take up glucose without it. That's the problem with diabetes mellitus. Without insulin, imagine that you're basically just like some poor little street urchin waif in Mexico City or someplace like that, all right? And you're basically starving to death, but there's a table in front of you just set with amazing food, all this great food in front of you, but you don't have access to it. You're starving. There's all this food here and you don't have access to it. That's what happens in diabetes. Without insulin, you're like that little sort of street urchin that's basically starving because you don't have access to what? The glucose, all right? All the glucose ends up where? In the bloodstream, just stays in the bloodstream. That's why your blood sugar levels end up going up. But intracellular levels of glucose would be down because you don't have access to it. And without having access to glucose, they have no choice but to try to burn what? Fats. And that's why you end up with the ketoacidosis, for example, in people that have uncontrolled diabetes mellitus, because they're forced to have to rely as much as they can on burning fats. So it's promoting lipogenesis. What is lipogenesis? Is lipogenesis the production of fats or the burning of fats?
Production.
It would be the production, right? Because lipo is referring to fats, and genesis means what?
Beginning.
Genesis itself, beginnings.
Oh, neo was new.
Neo meant new. When we talk about gluconeogenesis, that was sugar new beginnings. But lipogenesis is just fat beginnings. Right, because excess sugar that you cannot use right away or store as glycogen will get converted into fats. What do we call the production of glycogen?
Glycogenesis.
Right, that should be up there too, right?
Yes.
Glycogenesis is the production of what?
Glycogen.
Glycogen. What is glycogen made up of?
Sugar.
What sugar?
Glucose.
Glucose. It's just a glucose polymer.
Wait, so where is the it's the okay, I'm confused myself.
That's because there's a lot of the same terms.
Yeah, there's the other one.
I know
The
it.
glucagon.
Yeah, I was like, where is that?
Yeah.
Next one.
That's the next
We're
one.
That'll
getting
be the
there.
next slide, please.
I saw that earlier too.
Okay.
That'll be next slide, please. So we'll talk about that. And again, I'm not going to ask about growth hormone for this. It does promote glucose uptake. It has an insulin-like effect, but again, there's not a whole lot of clinical relevance to it,
Okay.
like there was with insulin.
I'll just cross that out.
But it does explain why people that are having growth spurts tend to grow more, again, because growth hormone does have that same kind of effect, increasing glucose uptake. Now we get to talk about the absorptive state. Now somebody can talk about, post-absorptive state.
Fun.
Tell me when you would enter the post-absorptive state. Right, so that you would enter the absorptive state usually 3 to 4 hours
Later.
after a meal. It just depends on the size of your meal, really, doesn't it?
Yes.
And also, it would also depend, I know we're painting with a very broad brush here, but it would also depend on how much carb was in the foods that you were eating. Because if you were eating, like who's that, like an Atkins kind of like no carb kind of diet, or one of those like paleo kind of things where you're just eating some animal you just killed. Is that pretty much the paleo diet that you killed with your own hands? I think that's what you have to do, right? You just bite the neck with your teeth. That's paleo diet. So if there's very little carb in your diet, you're going to enter the post-absorptive state a lot sooner, almost immediately, right? Because you're still going to have what hormone is responsible for the post-absorptive state?
Glucagon.
Glucagon. And how long will you remain in this post-absorptive state?
Until your next meal.
Until your next meal.
So 3 to 4.
The hormone glucagon has one main target. There's only really one organ that's really affected by glucagon.
Liver.
The liver. Glucagon almost exclusively affects what?
The liver.
The liver. Because the liver is where you have excess glucose stored for body-wide distribution in the form of glycogen. Remember, we also said that in the absorptive state, your muscles will store glucose as glycogen. But when muscles store glucose as glycogen, it is for their own selfish needs. They will not release it in the bloodstream if everybody else wants some. No, they're very selfish. But when they talk about athletes who are going to do an endurance event that do carb loading, have you heard of that sort of phenomenon? They're carb loading. What they're trying to do is be in that absorptive state and get their muscles to store as much glucose as glycogen to get them through their next race, their next performance. Oh, and this is where those horrible terms are very similar because, as you're mentioning, the hormone glucagon will promote glycogenolysis. Glycogenolysis is different than glycogenesis, right? Glycogenesis is making new glycogen, right? Glycogenolysis, what's that lysis?
Breakdown.
To break down, to split.
Glycogenolysis and glycolysis.
Sorry. Yeah.
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 Just remember that lysis is to do.
Death.
I'm not thinking about
To break
cytotoxic
down.
cells.
Lysis really is splitting, right?
I'm not thinking about cytotoxic
Yeah.
cells, then I see here lysis.
Absolutely. That's a good image to have in your mind. Did everybody hear that?
What?
Can you say that again?
Oh, whenever I see the word lysis, I only remember breakdown because I think of cytotoxic cells.
Yeah,
whenever
I'm
it
like
breaks it
death by
down.
like.
Mhm. Death by lysis, by
See?
splitting them apart.
Yeah, that's why I said death, not because I'm dark. But
Mhm.
I am very.
So
My video.
glycogenolysis.
Yeah, because that's what we did. But...
Glycogenolysis is the breakdown of your glycogen storage forms, right? Because glycogen is where you stored your glucose. So glycogenolysis will start to release the sugar molecules, the glucose, into circulation to try to get your blood sugar level stabilized. But what if you have run out of glucose? What if you run out of glycogen? Forgive me here. What if you run out of glycogen? How can you get new sugar?
From your liver?
The liver can make new sugar by what process?
Glycogenesis.
I keep doing this, right?
Glycogenesis.
Right. Gluconeogenesis.
Gluconeo.
And again, all these terms that are similar: glyco, gluco, glico.
Is it gluco for glucagon? Why is it for glucose?
This is gluco for glucose here.
Glucose, not glucagon.
Right, there's no N in here. If there's a glycan, then it would have been glycogen here.
It's like a play on word.
Yeah. So
Glycogenesis.
glucose. Say that 5 times fast.
The second one, that's the breakdown of, you
Yeah.
said glucose, you said?
Yeah, this is the breakdown of glycogen.
Glycogen, there you go.
Oh.
Glucagon is just.
Oh, right.
Wait, so what's the
it's
difference between?
glycogenolysis.
Okay. Okay.
Oh, that's.
Oh, the word glycogen is in it anyway. so
Right,
you
the
just
word
remember that.
glycogen is in it.
Okay, you remember that, okay, that's perfect.
Oh, wow.
Okay, and then glucogenesis is the beginning of new.
Glycologist? Wait.
And then
Say it one more time.
Glycogenesis.
So, right, we can do this. We're professionals.
Glycolysis.
Glycogenolysis
Oh my
Glycogenolysis.
God.
is the breakdown of what? Glycogen.
So what's,
When you break down glycogen, what does it produce? Glucose. Because it's just a big branching chain of glucose molecules. That's all glycogen is.
say that a little
And the enzymes that do this just start clipping off sugars from the end.
Glycolysis?
Yeah.
What's glycolysis then?
Glycogen.
Glycolysis.
So what's the difference between glycolysis and
Wait.
glycogenolysis?
Glycogenesis, which one is that?
No, not that one.
Glycogenolysis is the breakdown of